Hi there, welcome back to this channel. In this video, we're going to be discussing intermolecular forces. Now, this is one of the concepts that you must understand to have a handy grasp of the chemical reactions that occur in organic chemistry. Now, recall that in our last video, we talked about electrovalent and covalent bonds, and we said that the electrovalent bonds are stronger than the covalent bond because of the electrostatic force of attraction that is holding them together. Hence, they have a higher boiling point and what? A higher solubility in water. Now we said also, as a classical saying, that like dissolve like. So meaning that a polar solvent will dissolve a polar solute, while a non-polar solute will dissolve a non-polar solvent. So that is to say that when a substance is polar, it's going to be able to dissolve in water. Is that okay? Or any other polar solvent. Now, the covalent bond is the sort of bond that exists between exists when atoms share electrons. Now, sometimes covalent bond might happen between substances that have different capacities for drawing electrons. That capacity for drawing electrons is known as electronegativity. Now, if a covalent compound, a covalent bond happens between two substances of there is significantly different electronegativities, there is going to be a phenomenon known as polarization. Now, I explained polarization in another video, so I'm going to link the video in the description so that you can see that video. Now, but listen, when a substance is having a greater electronegative value and it is bonding with another substance with which it has a greater electronegative value over, it is going to have a greater pull for electron. So when it has a greater pull for electron, it's going to actually polarize that bond and sort of look like it is having more electron to itself than the other bonding atom. All right, and this is what is going to lead us to the three types of intermolecular forces that we have. We have the dipole-dipole interaction as number one. Now let's discuss the dipole-dipole forces or dipole-dipole interactions. Now, what is a dipole-dipole interaction? Consider the molecule of hydrogen, the molecule of hydrogen chloride, the bond between hydrogen and chlorine. So, for example, hydrogen wants to bond with chlorine. And remember that chlorine has the Lewis structure of chlorine. If you don't know how to draw Lewis structure, I'm going to also link the video where I taught how to draw a Lewis structure in the video description. So the Lewis structure of hydrogen is like this, and it shows that it has one electron with which you want to pair, use in bonding. So if you want to bond with this, it's going to become this, which we represent with bonding line as HCl. Now, because we already know that this guy has a greater pull for electron, it is going to pull electron towards itself than hydrogen will. So because of that, because it's pulling more electron, it now looks as if that it has a higher amount of energy. You know that when you gain electron, you become negatively charged. So it looks like this guy has gained more electron to itself. So that's why it is having what is called a partial. This sigma minor, this is delta minus rather. Delta minus shows a partial charge, a partial negative charge. Now, because this guy looks like it has gained the total electron, this guy looks like it has lost the total electron, but it has not lost. Only that it has a weaker pull for the electron. So the electrons are enjoying more time with chlorine while they don't stay with hydrogen. So because of that, it's going to have a partial positive charge. Now, because of this phenomenon, this guy is going to seek to attract electron pair from another molecule elsewhere. And that's why we have intermolecular, because it is occurring between two or more molecules. And that is the concept of Lewis acid. Recall that Lewis described acid as a substance that is an electron pair acceptor. Of course, he said to form a coordinate covalent bond, but he says an electron pair acceptor. Why? This guy is going to seek to coordinate to another electron sufficient atom or electron sufficient center there. So it's going to begin to seek to coordinate to another electron sufficient atom in that molecule. And because it is all HCl that is present, so another molecule of HCl present here is going to begin to interact with it. Now recall that polarization will also happen here. So because polarization also happens here, it's going to seek to gain electron from this guy that is full of electrons. And this same guy, this other guy too, because it's feeling like it's electron deficient, is going to also seek to coordinate to this guy. And this bond here, first, this is called a dipole. This is what you call bond polarization. This is what you call a dipole. Now, what you now call a dipole-dipole interaction is this. Dipole-dipole interaction. This is a dipole interacting with this dipole. This dipole is interacting with this dipole. And what we have was a dipole-dipole interaction. All right. Now, this dipole-dipole interaction is quite a weaker force than the covalent. Remember that we said that the covalent bond has a bond energy of 4 to 12 kilojoules per mole, isn't it? But a dipole-dipole has a bond energy of we said covalent bond rather has a bond energy of 120 to 125 to 420 kilojoule per mole, while this one has a bond angle of 4 to 12 kilojoule per mole. So compare this. The dipole has 4 to 12 kilojoule per mole, while the covalent has 120 to 420 kilojoule per mole. So it's a weaker force of attraction, but it's intermolecular. It is happening, and that is why you can have the molecules of HCl stay together in liquid form. So this guy and this guy, dipole-dipole interaction has a weaker bond energy. Now, what is the next intermolecular force we are going to discuss is the London dispersion force, the London forces, or London dispersion forces. Now, in some textbooks, you see them as van der Waals forces. Van der Waals forces are generally all of these three. The three intermolecular forces we are going to discuss are called van der Waals forces, but they specifically refer to this one as van der Waals forces because we know that all the intermolecular forces are weak. So, van der Waals forces are weak, but this is the weakest of them all. And you're going to know why in just a moment. Now, when electrons move around an atom, there are certain times that electron distribution is not uniform. So since electrons at certain moments are not uniformly distributed, it means that there's going to be a time where there will be a momentary dipole, very weak dipole, a momentary dipole. So say, for example, in a particular molecule, there is a dipole, a weak dipole existing at the center there. Now, between a molecule A or a molecule X and Y, let's use X and Y. Now, and there's another dipole existing in the same molecule, in the same compound, and their dipoles coincide. The positive and negative coincide, and they come close to another. Now, what will happen is this: between this molecule X and Y, there's going to be a form of these weak dipoles will attract one another. Because they are attracting one another, they form what is called a partial positive charge and a partial negative charge as well. And so you have something like this: a D plus and a D minus, and that's for X, and a D minus here and a D plus, so that they interact. And this is what you call London dispersion forces. Now, it is momentary in nature. It is momentary. It doesn't happen all the time. It is momentary because it only happens when during moments when there is unequal distribution of electrons within the molecules. And this is what explains how the molecule of helium can be, liquefied at really low temperatures. So we said the dipole that is formed is momentary, means that it breaks off very quickly, and means that it has the least strength. It is the weakest It is the weakest of all bonds. In fact, the bond energy for London dispersion force is actually 4 and less, 4 kilojoule per mole. So compared to this or compared to this one is between 4 and 12. So you see that it has a lower bond energy. Now, the third type of bond is going to be the hydrogen bond. The number 3 is going to be the hydrogen bond. Now, number 1, hydrogen bond is not a bond between different molecules. It is not a polar. It is not a bond that forms a polar. That forms a formal, that gives rise to a formal charge. It is just in like manner as this. But the difference is that hydrogen bond only occurs when hydrogen is bonded to any of these electrovalent, any of these very electronegative compounds, element atoms, such as oxygen, nitrogen, and fluorine. Now, basically, most halides, but it has been mostly appertained with fluorine. So when hydrogen bonds with any of these, it is going to interact, it's going to form what is called an hydrogen bond or a hydrogen bond. Now, how does it do so? For example, this is the way the molecules of water interact inside water. The molecules, how they interact is this, that there is a bond between hydrogen and oxygen. Recall I talked about this in the covalent bonding video, the bonding video we did. So this guy, because it is very, very electronegative, oxygen is a very electronegative compound. So because it is very electronegative, the same way it did there is going to pull electron density towards itself, and this one is going to be almost electron deficient. Electron density is away from them. So because of that, it is what? Partially positive charge. Notice all of these are partial charges. So because of that, this one will seek to coordinate to another oxygen atom. So, and this one is also already bonded to another hydrogen. It's bonded to another hydrogen. Then this one will seek to coordinate what? To this hydrogen. So this hydrogen bond, this hydrogen bond. This one will also seek to coordinate to another. Recall that this one will also seek to coordinate to another oxygen. And this one seeks to coordinate to this one. So it is the bond between hydrogen, and when hydrogen is directly, notice it must be directly bonded to oxygen, or directly bonded to hydrogen, or directly bonded to what? Fluorine. When hydrogen is directly bonded to any of these, a hydrogen bond can occur. And in fact, the hydrogen bond is actually stronger than this and stronger than the dipole-dipole. In fact, the hydrogen bond has a bond energy between 10 to 40 kilojoules per mole. So compared to this, you see it is stronger, and we said this guy is weaker. In fact, the London dispersion forces, notice I said they must come together because the distance determining. In fact, the bond energy is that the force of attraction between this guy is directly proportional to the r raised to power 6, the sixth power of the distance between them. So you can see that the distance really has a lot to determine, has a big role to play in determining the London dispersion forces. So in fact, almost no energy is needed to break the London dispersion forces. And this is it for the 3 intermolecular forces that we have: the dipole-dipole interaction, the hydrogen bond, and the London dispersion forces. These are the forces that exist between molecules. See, we are going to consider the other concepts of inorganic chemistry. Make sure you do also subscribe to the channel, and so that you will not miss out on any of those videos. We're going to break it down as simply as possible. See you in the next video. Until then, stay blessed.